All right, listen up. Today, I'm going to let you in on one of the most elegant hacks in all of distributed systems. Seriously, this is the secret weapon that lets massive, global databases heal themselves without crashing the entire network. You are going to want to see this. Let's do it. So picture this. You've got this whole cluster of servers, everything's humming along, data is flowing, perfectly in sync. It's beautiful. And then the pager goes off. One of your servers just died. It just dropped right off the network. But hey, an hour later, it reboots itself and comes back online. So what now? How in the world does it catch up on everything it missed? Okay, quick refresher. Remember day 18? We talked about heartbeats. So we know how we knew the server was dead. The other servers just stopped hearing its pulse. They marked it offline, simple enough. And on day 19, we covered the gossip protocol, right? That's that nonstop chatter between all the healthy servers where they're constantly sharing every single update. New users, deleted photos, you name it. But here is the crisis. Our zombie server was offline for a full hour. It missed 60 minutes of that gossip. So its data is dangerously stale. I mean, it might think a user account exists that was actually deleted a half hour ago. This is a recipe for catastrophic data corruption. Total disaster. So how do we fix this? Well, the first, most obvious answer is also the absolute worst one. It leads you straight into what I like to call the terabyte traffic jam. So the brute force way is pretty simple. The server that just woke up asks a healthy one, hey, just send me all your data and I'll compare it line by line to what I've got. I mean, it sounds logical, doesn't it? It's dead wrong. Because all your data in any modern system isn't just a couple of files. We are talking about 10 terabytes at a minimum. Yeah, let's get a reality check. Sending 10 terabytes across your network just for a comparison? That's like trying to drive a massive, slow-moving garbage truck down a glowing neon superhighway that was built for light cycles. You're not just going to be slow, you're going to cause a system-wide traffic jam. The whole network just grinds to a halt. It's an absolute catastrophe. You know, this whole process of finding and fixing these data differences, it actually has a name, anti-entropy. And that garbage truck approach, it is the absolute worst way to do it. So, if the garbage truck is out, what do? Well, this is where the real magic comes in. This is the massive performance hack that powers everything from Amazon's DynamoDB to Bitcoin itself. It's called a Merkle tree. Here is the kicker. This is the part that changes the entire game. We are never going to compare the data itself. We're going to compare tiny cryptographic hashes of the data. Now, the textbook definition is that every parent node in the tree is just a hash of its children. But let's be real. What does that actually mean? Let's build a better mental model. I want you to imagine a glowing neon pyramid. At the very bottom, you have millions of these tiny little data cubes. Each one is a piece of our data. And they merge upwards, level by level, until at the very peak of this pyramid, you have one single shining orb. That's the root hash. It represents everything below it. So how do we build this thing? It's actually beautifully simple. Step 1, we break all our data into small, manageable blocks. Step 2, we create a unique hash for every single one of those blocks. Step 3, we take pairs of those new hashes and we hash them together. And finally, step 4, you just keep repeating step 3, building up the pyramid until only one single hash remains at the top, the root hash. Okay, let's actually see this in action. On the left, you've got your raw data blocks. And then on the right, we've just created a hash for each one. See? Simple as that. Now just keep an eye on things, because an inconsistency is going to pop up, and we'll see how that changes everything. Now watch this. We take those hashes from that first layer, and we hash them together to create the next layer up. We just keep repeating that process, going up and up the pyramid, until, bam, we get a single root hash at the very top that represents the state of all the data below it. Okay, so the pyramid is built. Now for the magic trick. How does this thing help us find one single bad byte in a 10 terabyte database without that traffic jam? Well, this is the dream scenario. Our server wakes up, it asks a healthy server for its root hash. They compare. They both have 5357, they match. That's it. We now know with certainty that every single byte of data is identical on both machines. Check complete in a millisecond. No traffic jam, we're done. But plot twist, while our server was offline, a user deleted something. So, on all the healthy servers, one of those tiny data cubes at the very bottom of the pyramid has now changed. You can see it here. It's glowing red. And this is the absolute genius of the Merkle tree.
that one tiny red cube at the bottom, it doesn't stay contained. Because its parent hash is calculated from it, that parent hash also changes, and then its parent changes. The change cascades, like a red alert shooting straight up one branch of the tree, changing every single hash on its path, all the way to the root.
So now our revived server A still has its old root hash, 5357, but the healthy server B, with that one tiny change, now has a completely different root hash, 9213. Mismatch, that's our trigger. We know the data is different somewhere, and now the search is on. So how does the search work? It is lightning fast. The root hashes don't match, right? So we go one level down and we compare their children. Now look at the tree. The hashes on the left branch, they match, perfect. We can now completely ignore that entire half of the database. So we just follow the mismatch down the right branch and we repeat the process. We just keep descending level by level, narrowing our search exponentially until we find the exact data block that's different. Then we only sync that one tiny block. That's it. This technique is just insanely powerful, but it also sets us up for our next big challenge. What about data that isn't even there in the first place? I mean, just stop and think about what we've accomplished. Our database can now heal itself from huge outages. A server comes back online after being down for an hour, and within seconds, it pinpoints exactly what it missed. And it does it by transferring just kilobytes of data instead of 10 terabytes. But this brings up a whole new problem. We're amazing at finding data that exists but is inconsistent. But what happens if a user searches for a username that was never even created? How do we stop the database from wasting precious time and energy scanning billions of records for something that isn't even there? Well, tomorrow on day 23, we're going to solve that exact problem. We are building Bloom filters. You're not going to want to miss this one. Make sure you hit subscribe.